Okay, everybody. Hello and welcome back. A few housekeeping items that I noticed last time there were folks, Zoom refugees, sorry for those of you out there who were concerned about and were concerned hadn't been addressed yet. So I will just say several of you have told me that question 16 on the exam, the right answer is apparently not getting you any points. I don't know why that's happening. It clearly shouldn't be happening. So I will fix that. If you haven't observed already, I have made it so that you can go into the exam, see your responses, see what the correct answer is, see the items that you missed. Each question should provide access to an embedded video, which will have my explanation for why what the right answer is and why it's correct. There are a few folks who have not yet taken the exam due to emergency situations, so please be circumspect in your use of those videos and those questions. Please do not copy them and paste them into various internet venues like Chegg to give unfair advantage to other folks. I don't expect that you'll do that. I'm just going on the record as having said so. Someone is asking what was the correct answer for 16. I have no idea. I haven't looked at it since I wrote it. So it's the correct answer is the one that, I think it's marked right as correct, right? The correct, what was it, E or Z? I forget. I think it was E. Yeah. Correct answer for 16 is E, and for some reason it's not giving you the points. As I said, I will fix that. And then what else? There was something else. Finally, towards the end of today's lecture, I'm going to use that Molecules app, and I know it's difficult for folks at home to see it. I've tried optimizing the shared screen for video display, and what that actually does is it makes the video display blurry for the folks at home, which is exactly not what you want to do. So I will try when we get there to tilt my computer camera up so you can vaguely see the screen up at the top. I'm sorry that you'll have a substandard experience, those of you who are at home. However, we will be recording this on both Zoom and YouTube so that you can go after the fact and see it perhaps more clearly afterwards, and I apologize for that. Also, we will continue to be flexible with study guide due dates because we're not finishing Chapter 4 today. So I will adjust backwards the due dates for 4 and 5, and you can assume that everything will be similarly delayed from here on out. I'm sorry, so hopefully that's okay. Oh yeah, someone on the chat is encouraging me to encourage you to like. Don't forget to like, comment, subscribe, and hit the notification bell for the next release. Please don't worry about subscribing. You got better things to do. And no, my channel is not monetized, so I'm not practicing priestcraft. Okay. Not monetized yet. I guess we could still go viral. But who's ever heard of an OChem channel that went viral? Funny. That's right. All right. So let's begin. And I want to begin with a little bit of information on hyperconjugation. Now, some of you I know have been into the office with me or on Zoom office hours and have heard this explanation before. I apologize, but it's been useful enough in those contexts that I wanted everybody to have a chance to hear it. We have introduced hyperconjugation as the explanation for why the staggered conformation of ethane is more stable than the eclipsed conformation. And that's sort of a so what? If hyperconjugation only explains that, then what's the point of knowing it? Can't you just memorize that the staggered conformation is more stable than the eclipsed conformation? And the answer is sure. But there are lots of situations in the future where you're going to need hyperconjugation more to explain why things happen, and this, I thought, was a convenient place to introduce it. I want to just show you one situation, and you can go back to the notes from last time to see how we applied hyperconjugation to staggered versus eclipsed. But I want to show you a situation that's a little bit more important, a little bit more interesting. All right. So, and there are other examples. I'm going to stick with the simple one that I did last time. This may be, if you've been in to ask about this, I'm sorry, this will be a repeat. But one of the things I learned, actually, that when you're doing public speaking of any kind, it's always okay to tell people things they already know because it makes them feel good. So anyway, if you already know this, then feel good. And if you don't, you'll feel good soon because then you will know it. So if we looked at this carbocation, and I'll draw it from above, and I asked you, based on what we've developed so far in class, our combination of MO theory and valence bond theory, if I asked you what the LUMO of that carbocation was, you would hopefully have told me that it was the empty p orbital on the carbon. Now, if that seems strange or funny to you, or you're not sure why that's the case, you need to go back and look at the MO theory study guide and brush up on that. And you would predict that if we reacted this carbocation with some nucleophile, HOMO attacks LUMO, you would predict the nucleophile would attack the positively charged carbon, dumping its electron density into the empty p orbital to make a new sigma bond. And I guess highlighted in red is that new sigma bond. And that, in fact, is observed all the time. So, yep, that is a reasonable product. But we also observe, somewhat unexpectedly, that the nucleophile can actually remove a proton from a carbon adjacent to the positive charge and make a new pi bond between the positively charged carbon and the adjacent carbon. This is the new pi bond that was made. And we observe that all the time too. And it's okay if you're having a hard time seeing where this product comes from. We'll deal with that in Chapter 7. The point is we have evidence that the nucleophile not only can attack the carbon, but also the adjacent hydrogen. Okay, but what about HOMO attacks LUMO? What about that being the foundation of OChem? The LUMO is on the carbon, so what has the adjacent hydrogen got to do with anything? And this is where we're going to need sort of a patch on our MO theory, valence bond theory approach. Pure molecular orbital theory actually provides a pretty satisfying answer. Remember that pure MO theory is where we make molecular orbitals from combinations of all the atomic orbitals, and we generate these MOs, and they are delocalized through the whole molecule so that a single pair of electrons will be spread out over much of the entire molecule. A classic example of that was what we did at the beginning of class, talking about methane and how you could combine the 1s orbitals from each of the hydrogens with the 2s orbital on carbon to get this bonding molecular orbital. Which bond is it? That question is meaningless in MO theory because there are no bonds in MO theory, just electrons delocalized over the molecule. And though that was cool, we saw that it was kind of complicated and maybe unnecessary in most cases. And so we said we were going to focus on our hybrid approach where we think about bonds as being two electrons shared in a sigma or pi bonding orbital between two atoms, and then there's an associated empty anti-bonding orbital higher in energy. This is going to be a case where we're going to need some other kind of patch to get us to the answer that MO theory gives us, because if you calculate what the LUMO for this molecule is, as I've done recently, what you see is that, yes, it is mostly the empty p orbital on the positively charged carbon. Here, color again means sign of the wave function, but some of the LUMO is actually out on those adjacent hydrogens. And interestingly, it has this phase relationship. They're out of phase or opposite wave function sign with the lobe that's on that carbon, on that central positively charged carbon. And this provides a nice explanation for why we observe both of the products indicated here, because if you say that the LUMO, the calculated LUMO from MO theory, is on both the adjacent hydrogens and the positively charged carbon, then it's not such a stretch to imagine either product forming. And as I said, it's okay if you're not totally sure where this comes from. Just understand that the nucleophile stole a proton from the carbon adjacent to the positive charge. So how are we going to get, go ahead.
So I was just wondering, do the hydrogens ever flip between carbons and like put the positive charge on the other carbons then?
So an interesting question is, can a hydrogen sort of lean over and put the positive charge on this carbon? The answer is yes. That's called carbocation rearrangement. We'll get to it in chapter 9. There's a reason why it wouldn't be favorable for this molecule, but I'm going to punt on that until later. Yeah. Others? All right. Why is the p orbital out of phase with the ones on the edge? I will show you that. For now, just accept that this is the result from MO theory. That's a silly thing, but it is. So we're going to need some kind of patch or bridge, however you want to think about it, to get from our simplified approach to the answer that gives us a more reasonable explanation for what we observe. And that patch is something called hyperconjugation. Hyperconjugation originally arose from this idea in valence bond theory that you could actually make resonance structures that involved moving sigma bonds. In other words, some people thought about this so-called no-bond resonance structure where you take the electrons from the sigma bond and make them into a pi bond between the two carbons. And then, of course, the hydrogen would be hanging out here. Nothing moves in terms of the atoms, but the idea that the electrons on that sigma bond might be partially delocalized into where the positive charge is. So that was a valence bond theory concept, and actually it provides a decent explanation for where this alkene product comes from. And it gives you the prediction that this proton adjacent to the positive charge should be somewhat acidic, and it is. But how do we apply that in a molecular orbital theory sense? In hyperconjugation, we're going to mix sigma bonding orbitals or maybe lone pairs with empty antibonding or non-bonding orbitals. Like, say, a sigma star or a pi star or an empty p orbital. So bear with me for just a second. Do you remember how we talked about a sigma bond between two carbons as coming from taking an sp3 orbital on one carbon and an sp3 orbital on another carbon and adding them together plus and minus to get both a sigma bonding orbital and a sigma star antibonding orbital? And we got the sigma bonding orbital, again, by overlapping the sp3 orbitals on either carbon together in phase to get the sigma bonding orbital, and then the minus combination was the sigma star. And we don't need to draw that because we've already talked about it. Conceptually, this involved taking the two sp3 orbitals that were at similar energy, mixing them together. Here is the energy of the new sigma bonding orbital, and this is general in chemistry. Mix two orbitals together, you get one that's lower and another that's higher. And usually the one that's higher is higher up than the one that's lower is low. That's a terrible way of saying it. I haven't thought of a better way to do it. Relative to your starting point, the sigma star is more destabilized than the sigma is stabilized. But fortunately that's okay, because for our sigma bonds, we only had 2 electrons. We filled the sigma bonding orbital and the sigma star was empty. The math of MO theory doesn't change just because your starting orbitals are different. All right? So let's look at our carbocation again. I guess I can redraw it. And I'm only going to draw one of the adjacent carbon-hydrogen bonds. Here is the empty p orbital. How many times are we going to draw this? Many more, it would seem. So let's put ourselves in the plane of the board and look down the carbon-carbon bond. We would see that that carbon-hydrogen bond pointing up out of the page is lined up with the empty p orbital on the positively charged carbon. So this would sort of be what we would observe, and then I guess those other, those aren't hydrogens, those are methyl groups. All right. Viewed from the side, we might see that the filled carbon-hydrogen sigma bonding orbital was lined up with and overlapping side to side with the empty p orbital. And side to side overlap leads to pi-type molecular orbitals. So what would happen if we took that sigma bonding orbital and mixed it together, plus or minus, with the 2p orbital? We would predict that we could do that and we would get an MO1 that's lower in energy and an MO2 that's higher in energy. So let's see what that would look like. I will point out that if we make an energy diagram here, and we'd point out that the sigma bonding orbital is way lower in energy than the empty 2p orbital, because the empty p orbital is not involved in a bond. When two orbitals are far apart in energy and you try to mix them, they don't mix together as well as if they were close in energy. So the new lower energy MO1 is not actually that much lower than the sigma star. I'm sorry, than the sigma bonding orbital. It's a little bit lower. And the high energy antibonding MO2 is only a little bit higher in energy than an empty p orbital. Nevertheless, in this case, the p orbital was empty, the sigma orbital was filled. Mixing them together does allow those electrons that were in the carbon-hydrogen sigma bonding orbital to spread out and to lower themselves in energy. It's true that the antibonding orbital, or rather the 2p orbital, gets bumped up higher in energy, but who cares because it's empty, right? Let's see how these might look. Let's consider the plus option, sigma CH plus 2p. Here's your positive charge. So if we added them together in phase, that would look like this. And it turns out this is going to look mostly like a sigma bonding orbital. I'm sorry, it's going to look mostly like a carbon-hydrogen sigma bonding orbital, but with some of those electrons spread out onto the adjacent positively charged carbon. So if I were to draw what this actually looks like, it would be something like this. Oops. Guess I better keep my colors consistent. And if you look at that, it almost looks like something, it almost looks like a sigma bonding orbital between carbon and hydrogen that's trying to be a pi bond. It almost looks spread out enough to have some pi bonding character. And that actually is the same thing as this no bond resonance structure told us, that we might have some pi bond character between those two carbons. Okay, so one consequence of hyperconjugation is that the electrons from the filled orbital spread out toward where the empty orbital was. And therefore, because they're spread out, they go lower in energy, and that's a stabilizing effect. Now, what about the out-of-phase combination, the sigma CH minus 2p, or vice versa? This is going to look exactly like you would expect. That is, it's going to be mostly an empty p orbital. And then on the adjacent carbon-hydrogen, you're going to have some amount of orbital there, but because this is the minus combination, there has to be a node in between them, and the phase has got to be different, or rather the wave function sign has to switch across the node. Now, this was a question I think, Isaac, at home you asked, why is the p orbital out of phase with the thing on the adjacent carbon? This is why, because that comes from the minus combination. So this would be our, up here would be our MO1, and then this would be our MO2, all right? Or our LUMO, and the LUMO would be out not only on the positively charged carbon, but also on the adjacent hydrogen, so that a nucleophile could choose to attack here or there. Yes?
If you were to substitute a lone pair for the carbon-hydrogen sigma bond, would it be the same thing?
Yeah, if you were to imagine the carbon-hydrogen bond isn't there and it's just a lone pair on this atom, what do you think that looks like? What does a lone pair overlapping with empty p orbital on the other carbon look like? What you've proposed is actually just the resonance structure of the pi bond. So yeah, if you have a lone pair adjacent to an empty p orbital, you've got the chance for actually a full-on pi bond. Okay, other questions? Yeah?
What about hyperconjugation where you have a sigma bond and then maybe a pi star?
Sigma bond with a pi star? Yeah, I can show you a quick example of that. I just want to point out that the MO theory picture, because there's adjacent carbon-hydrogen bonds on all of the carbons surrounding that central carbon, the MO picture shows the LUMO spreading out onto all of those carbons. So we only considered one of those, but actually you would consider all three of them. And so this gets to consequence 2, or 3 rather, of hyperconjugation. So we said electrons from the bond spread out, they go lower in energy, and then 3, the LUMO spreads out toward where the filled orbital was. Okay. So we used this, okay, we'll pause there. A question was asked, what if you were trying to deal with a carbon-hydrogen bond adjacent to a pi star. So here's a pi star, the LUMO of a carbonyl compound. And the question is, can we overlap an adjacent carbon-hydrogen bond with the pi star? This is the filled carbon-hydrogen sigma. This is the empty carbon-oxygen pi star. Yes. The sigma plus pi star combination, I'm not going to draw, but that would tell us there's probably some pi character in the carbon-carbon bond. That is, these electrons here are spread out a little bit towards the LUMO, or towards the empty orbital. And that would also, the pi minus sigma star would tell us that the LUMO is spread out onto the adjacent CH. I'm not going to require you to go through in detail like we did here. It is enough for you to recognize that when you have a filled orbital adjacent to an empty orbital, the electrons in the filled orbital delocalize a little bit towards the empty orbital, and the LUMO, or the empty orbital, spreads out onto where the filled orbital was. What this would tell you is that if you are a nucleophile and you get this carbonyl compound, you could attack at the carbonyl carbon or at the adjacent proton. And that's 352 chemistry, and that's like a whole month or more of 352, which you now understand why it happens. And it's because of hyperconjugation. Yes?
Just to clarify, just in the example we talked about the last class, we were talking about the staggered versus eclipse. Because obviously, in both those situations, you have like antibody and you have bonding orbitals. So is it just in terms of the orientation with the staggered that those are going to be lining up better, so that's where you're going to get that hyperconjugation happening?
Yeah, so the question is, how does this apply to staggered versus eclipsed, and does it have to do with the orbitals that align? Yes. In the staggered conformation, the carbon-hydrogen sigma star on our first atom, which is filled, when we're in the staggered conformation, it lines up with perfectly side to side with the sigma star of the adjacent carbon-hydrogen bond, of the proton that it's anti to. This leads to sigma plus or minus sigma star, both of that mixing, but you've only got 2 electrons. So you're in this classical situation where the electrons in the bonding orbital get to spread out and go lower. The anti-bonding orbital, the sigma star, goes up higher in energy, but who cares because it's empty, right? And then, so that's one reason why staggered is more stable. Another reason why the eclipsed is less stable is because even though the eclipsed features side-to-side alignment of orbitals too, both of those are filled. So when you do the math of sigma plus or minus sigma, you have 4 electrons, right? Here's a sigma bond, there's a sigma bond, here's your new MO1, and here's your even higher in energy MO2, and because you've got 4 electrons, you populate both of them, and that's destabilizing. This was what we called, I think, last time, closed shell repulsion. And it's why 2 filled orbitals that line up with each other, that's a repulsive interaction, because you're going to destabilize the electrons. Okay? Other questions? To clarify, when we determine hyperconjugation, do we compare molecular or atomic orbitals? I'm not sure I can answer that generally. In the case for staggered versus eclipsed, we were dealing with 2 different MOs. One the sigma bonding orbital on this carbon, and then the sigma star anti-bonding orbital on the adjacent carbon. However, in the example we started with, we were considering a sigma bonding orbital on one carbon with an empty atomic orbital on the adjacent carbon. So it will vary. The pattern you're looking for hyperconjugation, though, is filled orbital adjacent to an empty orbital. So that's going to make it, I hope anyway, hyperconjugation is going to grease the wheels a little bit as we try to learn organic chemistry. We're going to use it to connect the simplicity of our hybrid MO theory and valence bond theory approach with higher level calculations that lead to useful predictions. In 352, you were going to learn that protons adjacent to carbonyls are more acidic than protons that are not adjacent to carbonyls. In fact, this may have been an example we did in the acid-base chapter. The pKa of this proton adjacent to the carbonyl is about 20, which is 20 orders of magnitude less, that is more acidic, than a proton that's not adjacent to a carbonyl. In rationalizing acid-base stability, we talked about resonance stabilization of the conjugate base, but you can also ask, why is that proton able to be removed in the first place? And the answer is some of the LUMO is actually there. All right, other questions? Yeah?
First example you gave us for the carbonyl is being attacked by the normal on the nuclear file. Let's see, right there.
Yeah?
And there's the two possibilities that
Uh-huh.
either the nucleophile forms a bond,
Uh-huh.
or it takes the hydrogen and the pi bond forms.
Yes.
Is that just like a flip of a coin?
It's a good question. How does this happen? What's the relative rates? It turns out with a high energy carbocation, the rates are comparable, and so you almost always get a mixture of products. There are other situations where you've got a similar competition where you can direct the reaction pretty reliably one way versus the other. And that's actually all of what chapter 7 and 8 are about. Yeah. Others? All right. Well, enough about hyperconjugation. I want to talk a little bit now about rotation around sigma bonds where it's not just as simple as ethane. So let's go a little bit more complicated. Let's look at butane. And I'm going to draw butane in a staggered conformation. We'll number the carbons 1, 2, 3, and 4. And we'll put ourselves in the plane of the board looking down. Oh, right. Somebody at home reminded me it'd be useful if I repeated the question because I know my mic doesn't pick up folks in the audience. Yeah, the question was really about whether it's possible to direct the nucleophile when it has a choice of attacking the LUMO at carbon versus hydrogen. Can you direct that? And the answer is not in this particular case, but sometimes, and we'll get to those examples in future chapters. Sorry about that. I'll try to be better about repeating the question. Anyway, as we look down this bond between carbons 2 and 3, we would see a methyl group on carbon 1 pointing straight up, and then a methyl group on carbon 2 pointing straight up, and then a methyl group on carbon 3 pointing straight down. This is an example of a staggered conformation. Note that about a sigma bond, there are between two sp3 hybridized carbons, there are 3 possible staggered conformations. This is one of them. We're going to call it anti, maybe abbreviate it with A. And the dihedral angle between the two methyl groups is 180 degrees. So it's the anti-conformation. Now, we could rotate let's say we rotate 120 degrees. We'll rotate the methyl group in the front 120 degrees, I don't know, counterclockwise, and see what that would do. That will trade us one staggered conformation for the other. We're going to keep the carbon in the back exactly in the same place. As we rotate counterclockwise, methyl group on carbon 2 should come here, and then protons at the other two positions. The dihedral angle between the methyl groups here is 60. This is still a staggered conformation, but we're going to call it gauche because the two methyl groups are gauche to each other. Incidentally, in terms of relative energies, which one, the staggered anti-conformation or the staggered gauche conformation, do you think is more stable? Anti. Why do you say that?
It's farther away from the CH3.
Right, because just to repeat, in the anti-conformation, the two largest groups on carbons 2 and 3 are as far apart from each other as they can be. We've got some political commentary going on around the chat. Something about anti-democrats being more stable. I will not share my political views because I don't want to alienate anybody, and I also think we should get used to having conversations with people with whom we disagree, but perhaps not in organic chemistry class. This would be the side view of this particular gauche conformation. And if you remember that methyl groups actually involve carbon-hydrogen bonds, then it will be a little bit clearer that in this gauche conformation, those carbon-hydrogen bonds can start to bump into each other. A methyl group is much larger than it appears on paper, and you start to get what's called steric repulsion. It's not exactly the same thing as closed shell repulsion. It's just sort of Coulombic electron repulsion as you have two groups with electrons and they get close enough to feel each other. Incidentally, steric hindrance is why your hand cannot go through the table or the desk or the pen, because your electrons repel the electrons in the table or the desk or the pen. Next time you walk into a crowded place, presumably after the pandemic, right? Nobody here goes over to the crazy Halloween party in Saratoga, right? That was a bad idea. Next time you're in a crowded place, you can say there's entirely too much steric hindrance in here for proper COVID precautions. And that will, if not get people to comply, it will at least make them look at you strangely, which can be just as rewarding. All right, if we rotated, and sometimes the steric repulsion is often cited as the origin of torsional strain. All that means is the gauche conformation is not as stable as the anti-conformation. If we rotate another 120 degrees, we will trade one gauche conformation for another. That's going to put the methyl group in the front to the right of the methyl group in the back. And what do you predict in terms of the relative energies of these two gauche conformations?
Probably the same.
Yeah, probably the same. Unless you're in what's called a chiral environment, you can't tell the difference between clockwise 60-degree angle and a counterclockwise 60-degree angle. So we'll call this gauche conformation 1 and gauche conformation 2. And of course, if we continued to rotate another 120 degrees, we would be back to our anti-conformation. All right. So if we were to put on an energy diagram and try to position these various conformations, we've got anti here, gauche 1 here, gauche 2 here. Anti, we've said, is lowest in energy because it has minimal steric repulsion, as those methyl groups are as far apart as possible. And then the gauche conformations should be equal in energy and both higher in energy than the anti-conformation. And I actually wanted to put them a little bit closer together. All right. And to facilitate our discussion, I'm going to copy and paste some of these conformations that we've drawn up here so that we don't have to keep going back up and checking what they look like. All right, that'll work. It's not quite as cool as Tony Stark with his three-dimensional holographic images and stuff, but when you get excited about what you can get excited about when you're my age. So, ooh, that's fun. All right, let's talk about interchange between each of these gauche conformations should require. Each of these staggered conformations should require an eclipsed conformation. Right? And so let's talk about those eclipse conformations and what their energy should be. As I rotate this orange methyl group through, it's going to be eclipsed with a hydrogen. So I'm going to cheat now. It actually didn't save me hardly any time. We'll put the methyl group here so that it looks like it's eclipsed. It's not perhaps perfect. In this eclipsed 1 conformation, you have 2 times where methyl groups and hydrogens are eclipsed with each other. Then going from gauche conformation 1 to to gauche conformation 2, we should go through an eclipse conformation where all of the carbon-hydrogen bonds are eclipsed with each other and where the 2 methyl groups are eclipsed with each other. So we have 1 methyl-methyl eclipsed. Then going from gauche conformation 2 back to the anti-conformation, it looks like we ought to go through another case where methyl groups are eclipsed with hydrogens. A lot of stuff going on there. Let's talk about those eclipsed conformations. Which do you think is the worst? Methyl-methyl eclipse, the 2 biggest things eclipsed with each other. How much worse than the others? Who knows? But what about the relative energies of these remaining 2? About the same, right? They've got to be the same. So because they have the same number of gauche interactions. So we'll go ahead and pull those down there. So now we can actually draw an energy diagram that shows us how the energy changes as we rotate around that carbon. And this allows us to make some interesting predictions. First, go down there, and those 2 lines would be connected with each other. First, if everything was in equilibrium, you would expect the anti-conformation to dominate. but the two gauche conformations to be similar. Now, think about this. Suppose you're in gauche conformation 1. What is the lowest energy pathway to get to gauche conformation 2? And just to pause, yes, yes, Preston, the methyl eclipsed is higher in energy than the hydrogen methyl eclipsed.
Wouldn't it be to go all the way back?
Yeah, you're not going to go over the tallest hill. Instead, you're going to go back to the anti and then up over this barrier to the other gauche conformation. The ability to go from one staggered conformation to another will depend on the heights of these barriers. And if you don't have enough kinetic energy at room temperature or at whatever temperature you're at to traverse this barrier, it'll be slower to go over the lower energy ones than the higher energy ones. Now, your book will contain some information about the absolute numbers here. I don't care what they are. What's important is that you could rank them in order of energy. Interestingly, it's interesting to ask what is the equilibrium like at various temperatures? Could you be at a temperature where you could freeze out only the anti-conformation? And to see whether that's possible, you can compare the height of these barriers, which are on the order of 5 to 10 kilocalories per mole, maybe less, but you can look at the numbers in your book. You can calculate the average kinetic energy of molecules at temperature T by actually multiplying the temperature by the universal gas constant. That gives you kilocalories per mole. Or if you want kilocalories per molecule, you can do by the Boltzmann constant. But if this number is bigger than the height of the barrier, that means you can freely traverse from one to the other all the way back. If it's lower than the height of the barrier, then that means that it's going to be slow to go from one versus the other. Question, is this why proteins denature? There's a lot of interesting answers to that question, but in effect, yes, the protein has to have enough kinetic energy in order to overcome rotational barriers and unfold. There's other things going on too, but that is certainly one of the things that has to happen. All right. Sorry, I'm just trying to think. I think instead of showing you the movie, I'm going to set up an interesting problem for you to think about over the weekend. And oops, didn't want to do that. I want you to think about how this energy landscape would change if we started putting more things on one of these carbons. Say, for example, we put an OH group on the back carbon in addition to the methyl carbon. Now, I'm not going to draw all these other staggered and eclipsed conformations for you. You can go ahead and do that, and if you can copy and paste, it's just going to require you to erase some stuff. But see if you can rank the 3 staggered conformations in energy. It's not clear anymore which one should be called anti. It depends on which groups you're interested in. And then rank the 3 eclipsed conformations and see if you can sort of predict what the energy landscape of this molecule looks like. If you want to see a movie of how butane rotates, what I will do is I'll just copy the section of the noon lecture where we did that and just append it to the end of this one on YouTube and I don't think I can do that on Zoom, but I can certainly do it on YouTube and you can check it out there. As I said at the beginning, study guides 4 and 5 are not due this weekend. We haven't finished chapter 4 yet. I will delay those, and I will also fix question 16 on the exam. Have a great weekend.